My name is Jim Nitterauer. I am a senior security specialist at AppRiver. AppRiver is a web and spam filtering service. We are based out of Gulf Breeze, Florida. We have 250 employees and 8 offices worldwide. So today's talk is entitled DNS Dark Matter Discovery. There's evil in those queries. So before we get going here too far, of course my mouse isn't deciding to work, so I'll have to do it manually. The information that I'm presenting today in this talk is intended to help you make your environment more secure, and it's not intended for unethical purposes or unethical use. Concepts presented today are in no way meant to imply original research on my part or part of my employer. Any information presented is gathered from public and private sources with the proper references where applicable. So, AppRiver, what do? We filter spam for about 10 million email boxes worldwide. We're in 10 data centers worldwide now. We run a hosted exchange environment that's a little over 400,000 mailboxes. So if you're an exchange administrator, send us your resume. We'll make your day. And then we also run a DNS filtering service. My area of expertise is deployment of infrastructure in the data centers and then securing that infrastructure, and then I work on the DNS team. So this talk was put together based on some information that we found in our DNS queries. We provide DNS service for about 30,000 endpoints, so those customers send a lot of DNS data our way. So, security is kind of a strange area, right? I was at a talk the other week, and somebody was telling me a little story. He said, "I'm thinking about security. This guy breaks into a house, cracks open the door, gets in the house. All of a sudden he hears this voice, 'Jesus is watching.'" The guy thinks, "Who is that? Is somebody in the house?" He looks around a little bit, couldn't find anything, keeps on walking through the house, gathering the stuff that he wants to steal from the home. Goes a little further, hears, "Jesus is watching." He looks around again, doesn't see anybody. Again, hears that, "Jesus is watching you." Turns around the corner and there's this parrot sitting in a cage on a perch. The guy goes, "Is that you making the noise?" Parrot goes, "Jesus is watching you." The guy goes, "What's your name?" He goes, "Moses." The guy goes, "Well, what kind of dumbass names a parrot Moses?" Bird goes, "Same dumbass that names a Rottweiler Jesus." So security comes from unexpected places. So most important thing for us in our security is looking at DNS, and that's pretty much what we're experts at. So today what we're going to do, I keep walking away from this mic. I'm used to walking around with a headset, so I'll have to stand close, and I move around a lot. We're going to do a quick review of how DNS works. Nothing too deep, but just to get an overview of how a DNS query flows through the DNS chain. We're going to cover some common DNS exploits that we see. Then we're going to look at some open source tools that we use to be able to uncover these exploits. Then we're going to examine some of the results that we got, and we're going to discuss some of these solutions in a little bit more detail, and then give you a chance to answer some questions. So first, what happens when DNS is horked? Now, I'm taking a class with Jeff Mann there today, and we're not supposed to use colloquialisms. So the word horked is something that I grew up with in the Pennsylvania area. It means broken or jacked up, screwed up, whatever. So how many of you remember what happened last year on October 21st? All right, the dying DNS attack, right? I get up 7:30 in the morning. I'm up at SkyDogCon in Nashville. Get this call from one of our network engineers. "All of our customers are calling. DNS isn't resolving for Twitter." Okay, great. The world's coming to an end. Twitter's not working. So I get on the internet and I look at some of our stuff, look at some of the logs that we're seeing. Turns out dying DNS was down. This went on throughout the entire day. And finally it came back online. But just the fact that that was down for that little bit of time and the amount of FUD that created. Now imagine if more of the internet went down. That botnet that was used to take that down was about 12% of the possible endpoints were used to take that DNS down. So the story behind that, who knows what the real story was behind who did that and what happened? Anybody? So apparently about May or June last year, one of the gamers at Xbox.com violated his terms of service. And he threw a fit. Didn't have much money, collected up enough money, and bought time on this Mirai botnet and went after Xbox. Well, guess who hosted Xbox's DNS? Dying DNS. They were taken out for that day, and the kid was eventually found out. So what we want to do is look at how can we protect our network from DNS attacks. So let's go through the DNS resolution process a little bit first. Initially, a local host, at step one, makes a DNS request. It hits the caching resolver. That can either be local or just outside your network. If that cache resolver has the answer, it replies with the answer back to the host, and that's the end of the query. If the cache resolver doesn't have the answer, it forwards it on to hopefully the root server, or it may go to a trusted forwarding server. And we'll talk a little bit later about securing your DNS so that you know who you're forwarding queries to. But ideally, it would forward to the root. The root servers return the name server that is responsible for the domain. Then the caching server goes and queries that top-level domain server, and then it goes and queries the authoritative domain server. So there's 7 steps, 8 steps actually, in the DNS process. So if you can kind of think about how DNS works from that perspective, you'll get a better idea of how to protect it. A couple of terms you'll hear when you're dealing with DNS, and you have to forgive me, I like to educate people when I talk because there's audiences that have every different level of technical experience, and there's a lot of young people and new people that are new in the field, a lot of older people that really know what they're doing. So I'm not doing this to insult anybody, I'm just doing this so people can get more familiar with the terminology. So one of the things we use in our DNS is called anycast routing. In IP routing, you can have an IP address exist in multiple locations, the same IP address, okay? So in our case, think of Google. We'll use Google as an example. Their name server, 8.8.8.8. It doesn't exist in one data center. It exists in about 70 data centers worldwide. When you type that in, your ISP has a BGP route that routes you to the closest instance of that 8.8.8.8. That way, if somebody takes out that node, it pulls it out of BGP and routes you to the next closest instant. A TTL is a time to live. How long does the record live in your DNS cache? Or how often do you have to requery DNS to get a new answer? DNSSEC is a protocol that was described for DNS security. It's actually got 2 RFCs that describe it, and it's used as a way to do a key exchange between a DNS client and a DNS server to validate that the name servers that you're actually getting responses from are authoritative for that domain. It's complicated and it's not used very often. It should be used more, but it's not. An NX domain is a way that a domain name server returns a response for a domain that it cannot find an answer for. A zone transfer is just what it says. It transfers zones between servers. Keep this in mind. Does anybody know what TCP port domain transfers go over? TCP port 53, right? TCP is required for zone transfers. So this is a vulnerability in DNS that a lot of people overlook, and I'll tell you why a little bit later. Authoritative name servers are simply a name server that is responsible for holding the master records for a particular zone. And a recursive resolver is one that does caching. It doesn't own any authoritative records. Some of the common DNS servers you're going to see out there will be Bind. Obviously, that's either an authoritative or a caching server. It's currently in version 9. We don't use it for very much. We use it for some zone transfers, but it's pretty bloated for a caching server, and it's very hard to manage. We use Unbound, on the other hand. This slide I didn't update. It's up to version 1.6.2. Unbound is really cool because it has caching and forwarding only, but it also has a feature built in where it does preemptive caching. So what that means is if your DNS server does a lot of caching resolution for a large number of domains, the DNS server will look at the TTLs in the cache, and before they expire, it will preemptively go out and refresh that cache so that your users don't take the hit on the lookup times. So we use it. It's very easy to use. The newest version, 1.6.2, has a new feature built into it, and I'll give you some homework here. Go look up what eDNS client subnet is. Okay? I gave a talk at NOLACON about it, so you should be able to find it, but look at what that is and how it might impact your privacy and your security when you're browsing on the internet. Microsoft DNS is used typically for AD. It supports forwarding. It will do zone. It will do authoritative zones. How many of you use AD DNS for your authoritative DNS? That's public-facing, internet-facing. Good. I'm proud of you. Yay! Everybody gets a gold star. If anybody asks you, if your boss says, I want to use Microsoft DNS for public-facing DNS, go buy him a drink and keep him drinking until he says no, okay? Simple DNS Plus, this is a good one for Windows. It's not involved with Active Directory, so you can host authoritative zones on it. You can use it for public-facing stuff. DNS Mask is one of the resolvers that you'll find in a lot of your home routers. DDWRT has it built in. It's really just a caching resolver. It can do some zones locally. One of the tools that we use, we're going to look at some of the tools that we use now to do our DNS analysis, Dig. How many of you have put Dig on Windows? Yeah, it's a great tool for Windows. So to do that, you go to isc.org, download the bind install. It's a zip file. Unzip it into a Windows directory, name it Dig, put that in your path. Don't run the installer. There's really no installer to run. And now you can use Dig in Windows to do your DNS lookups. Linux, you can install Dig through the bind utils package for whatever flavor of Linux you're using. So Dig usage is really easy to use. It doesn't require you to do things like change the name servers and do these three-layer things you would have to do with NS lookup. So Dig allows you to actually do one-line commands to pull data. And there's some useful options here. So the man options, obviously dig -h or -h will get you the help. If you do a plus trace, this is useful for troubleshooting your DNS. If you're ever having issues and you're trying to figure out, was my DNS resolving, or is the guy upstream, or some name server in the path not working, you can use the plus trace option with Dig, and it'll give you a result from every name server in the chain when it did the lookup, and you'll see where it would fail in that chain to do the lookups. This plus subnet is used to add a subnet to the EDNS option 8, so it will add the subnet in. So what you'll see if you query Google, for example, and use the plus subnet equals and put a different IP address in there, it'll return different results for the same name because it's geolocating the DNS based on the client subnet that's passed to it. You can use the -f file name, which will allow you to put a list of domains in a text file, for example, and you can run that through a name server and get all the results that name server gives. It's great for building up cache, for doing testing. And then you can do -x will get you reverse pointer lookups for that particular domain, so you don't have to worry about typing it in the right format. But I use it because it's way better than NS lookup. One of the other tools we use is Wireshark. It allows us to do DNS captures. It allows us to look at different parts of the DNS packets. Linux has a built-in TCP dump. Will create a PCAP file. You can just download it in Windows or Linux and use Wireshark to look at it. It has an example filter, so if you want to look at DNS traffic, just type in the filter DNS and hit enter. It'll light up green, and you'll see something like this where it'll just filter and show you all of your DNS traffic that's in a particular capture that you're doing. So you can also test your own DNS if you want to do this. Go out to dnsstuff.com. It's free to do this. It will tell you if there's any errors in your DNS anywhere. It'll go through all the name records. It'll go through the times that the name records will live, the SOA records or MX records. It'll make sure everything works the way it's supposed to. It's a great tool. So these are the kind of tools that we use. We'll talk about the open source tools that we use in our environment in a few minutes. But first I want to look at some of the exploits and the vulnerabilities that we see in DNS. So first one we saw were DNS amplification attacks. How many of you ever had these leveraged against you? Anybody? So you were the target?
Yes.
Yeah, not fun, right?
Also the source.
Yeah, so you can't be the source and the target at the same time, typically. So, well, yeah, if you have enough IPs, yes. If you're not, but the same IP can't be the source and the target at the same time unless it doesn't work very well. But the way this works is in DNS, if you send a DNS request, typically the DNS request itself, the packet's about 50 to 60 bytes. If you ask for the right record, and we can thank eDNS for this, right? You can get record lengths up to 4,096 bytes returned by DNS over UDP. If you do that, you can commandeer a botnet network, for example, and use hundreds of thousands of machines to send small queries to hundreds of thousands of endpoints. You spoof the source, right? Because UDP is stateless. The IP address doesn't care. It'll just send the data back to whatever IP address is in the IP header. And if you put the same IP address on all 100,000 nodes that are out there hitting those other servers, it's going to send all that traffic back to that one IP address, and it will take them down in a matter of seconds. The first one we saw that was generated, this was a Spam House outage in 2013. It was about 75 gigs of traffic that they were getting back then. That's pretty intense traffic. We don't see these too much anymore, but we can catch them with the setup I'm going to show you here. The other thing we see, this is a way that malware uses to generate domains. I call it slow DNS reflection, but the proper term is domain generation algorithms. Somebody will infect a machine through typically a drive-by download, a banner ad kind of thing. The malware will then sit there and generate a DNS lookup for a subdomain of a real registered domain, and it will send this out over the internet. But one of the things that it'll do is one of those domains, and there will be the legitimate subdomain that's getting the botnet command and control traffic. The problem is it's hard to see because all of these other domains that are generated are fuzzing the data so you can't hardly see what's going on. The other thing that this can be used for is those same servers can also exfiltrate data via DNS, and I'll show you that here in a little bit. Some of the other anomalies we see are bad DNS queries are improperly formatted. Things like .local queries that are sent out of your network. They should never leave your network, but they are. Malformed queries end up hitting our DNS. And you'll see in here there's some of them that are actually domain generation algorithms that are in this list of things that we see. And this is just a capture from one of our Graylog servers, one of the dashboards that we have. But it shows you that malware writers don't always take the time to write malware that makes properly formatted DNS requests. But you'll see these in queries. Another thing we see quite a lot are malformed DNS packets. Typically, these are sent out for one of two things. One is to take down a DNS server that's a specific target, right? So if somebody can generate enough DNS requests to or from a target DNS server, that DNS server will stop responding to legitimate requests. And then the other thing that they can be used for is to send data via DNS through a covert channel. It's called DNS tunneling. So we can see this in our Graylog and our logging instances too. I said earlier that data exfiltration via DNS can be done. This here is an example. The domain ps780.com. This is just one example of hundreds we've seen. This particular domain is a legitimate domain. It's registered. It has name servers. Those name servers answer with IP addresses. The problem is when those name servers also do other things. They strip off the subdomain that is added to the beginning of the domain name. The malware gets on to somebody's machine, finds the files that it's targeting, and then starts to slowly exfiltrate that data by generating encoded subdomains that are added on to the domain. That goes on through DNS. Nobody ever looks at it. Nobody ever sees it. The remote DNS server responds with an IP address. Everybody's happy. But at the same time, that remote server strips off the encoded part of the subdomain and reaggregates the data back on the other side. So it's a slow way of getting data out of a machine, but it can also be used to send botnet command and controls back and forth as well. And we've seen both instances happen. Another thing that we can do with our logging is we subscribe to some lists that tell us which IP addresses are compromised. In our case, we use F5 load balancers on our front end, so all of our DNS VIPs hit an F5 load balancer. Those load balancers use iRules to pull in these lists from an aggregated source, and when we see a packet that matches one of those, we can log it and we can drop that packet by comparison. So we see that through DNS and we're able to pick that up. The last DNS exploit that we see is actually supposed to be a fix for DNS amplification. So with DNS amplification, the fix that was put in place was basically if somebody asks an any query or any kind of large query, your DNS server can be set to respond and say, I'm not going to answer that on UDP, but send me a request on TCP. Makes sense, right? Because TCP then is a stateful connection if it's done correctly. So then you know who you're talking to. That lost my word. The site that you're connecting to remote site will actually connect. You'll know who they are because the IP address is in the TCP header, and everything should be good, right? Well, guess what? Hackers are smart. They figured out that if we just send half-open connections back over TCP, then we can cause the target server to shut down. Oh, well, maybe we can send some spoofed TCP packets with half-open connections back to a remote site that we want to target. So now suddenly you become the middleman and you're sending a SYNAC flood to somebody else on the network. So it's not a good position to be in. So you have to be careful, and you still have to rate limit TCP connections on the remote DNS server. And the last thing we see in DNS are DNS flood attacks. We don't see these too often anymore. These were probably the first attacks we saw about 3-4 years ago. The biggest one happened in late 2015. The one that we saw was against Ultra DNS. So there's a magazine out there that has content for, they call it a gentleman's magazine, and they decided to change their content. And they put out a press release about that in the morning, and that afternoon they were DDoSed. So Ultra DNS was taken down because somebody was attacking Playboy to announce their displeasure over their change in content. I thought it was pretty interesting. So how do we deal with the data that we generate, right, with our logs? Where is the data? The problem with data is in syslogs, it's very hard to get at, right? We don't think about it too often. We have these files and there's rows and rows of data. And we have event logs, RMS, DNS, debug logs, application logs. The data is everywhere. But what happens when the pressure's on and we have to find out what's going on at that particular moment? We don't have time to search through and do all these greps and figure out what's in our logs, right? We want a way to aggregate this information. We really need that data. It's not there. I can't read it. I can't find it, right? Boss saying, fix this, and you don't know what's going on. So what we're going to go over here is the log analysis process that we use, and this is not put out by us. This is typically what it was developed by the Elk stack, the people who put out the Elk stack. We needed a way to migrate our data, format the data into a useful format, ship it to a remote site, and then aggregate it and visualize the data. So our data comes from log sources, obviously. We can process that data by various means. One of the ways you could do it is with NXlog. One of the ways you could do it would be direct shipment. There's all kinds of ways you can do it. The data is then taken in by some sort of aggregator and indexed, and then a front end puts that data out to where you can visualize it and search it. So for log shipping, we use, in our case, on Windows servers, we use NXlog. Has anybody ever used that or worked with it? Really, I'm surprised. It is a great tool for shipping logs. It's a log router. Basically, you point it to a set of log files. You tell it what you want to do with those. That's called a transform. And then you tell it where you want to send those logs. So this runs as a small, thin service on a Windows machine. And you can point it to multiple logs and route the data to multiple remote destinations. So it's a great way to ship data in real time. You could use Logstash, but that has been changed around now to be, it's called Packetbeat now from the Elk stack, so they don't offer the Logstash Logstash anymore. You can use other valid shippers as well. In our case, we write F5I rules, so they use a language called TCL, but inside there we can actually ship data from the F5 over to our Graylog instances in real time. So this is just a screenshot of Graylog. Graylog is the log aggregation platform. You're familiar with Splunk, right? Splunk's commercial version is a great product for people that can afford to use it. Graylog is kind of the open source answer to that for people that can't afford to deal with Splunk. It's a developing product. We'll be giving a class tomorrow in the afternoon. Leonard Koopman is the founder of Graylog. He will be here tonight, and we'll be giving that class tomorrow afternoon. So if you're interested, it's a 4-hour class. I'll show you everything that we do and how to do it, and you'll walk away with some VMs that will actually do this for you. So Graylog is basically, in our case, we put it in a cluster. Cluster is behind F5 load balancer. We ship all our logs to a virtual interface on that load balancer. Graylog has the ability to work with Elasticsearch in the back end. You can install Elasticsearch as a separate instance. You can install it on the same machine. It's really up to you. Depends on how big you want your environment to be. And the big thing about Graylog is it supports a format that is proprietary to Graylog. It's called Graylog Extended Log Format. And it allows you to set up name value pairs and ship data in JSON format. So this gives you a whole lot more flexibility in how you can search and aggregate and look through data as opposed to looking at straight up syslog data. It has dashboard support. It's all open source. Databases that are created with Graylog can be accessed with other tools like Kibana. So this is an example of what a GELF packet looks like. You have to have some basic information in the header part of this JSON packet. You put the full message in, the timestamp, the level, and below that, then you can put in name value pairs that you define. So if you're using a programming interface, you can get a GELF library and then put out these name value pairs into that GELF packet that gets sent to the Graylog server. So this is an example of how I do it in TCL. It looks complicated, but really it's just a JSON packet that gets sent through the logging platform on the F5. Here we have the other nice thing about Graylog is it has something called Graylog Sidecar, which allows you through a single Graylog pane of glass to manage all of your endpoint inputs. You put the sidecar on, say, a Windows machine that has NXLog installed. Once you connect that to your Graylog instance, you can then manage what that logs from your Graylog instance. You don't have to go back to that remote machine to do it. Not a big deal when you're doing 2 or 3 machines, but when you're doing thousands of machines, it's a big deal. So this gives you the ability to set up what logs you can ship with your NXLog or Logstash or whatever you're using back to your Graylog instance. Elasticsearch, you're probably familiar with it. Graylog uses version 2 right now. It'll switch over to version 5 with the next release coming out next week. Basically, it's a distributed database. It's indexed across multiple clusters. It's made for very fast indexing and very fast searching, and it's expandable and pretty redundant. You can integrate it with Graylog, Kibana, Logstash, and NXLog. I'm not here to talk about Elasticsearch. It's just what we use. One of the other tools we use, this is a pretty interesting one. It's called PacketBeat. This is replacing Logstash. You install this as a service on Windows or Linux, and it has all of these built-in, basically, packet capture libraries into it, and it will actually ship data to wherever you tell it to go. So it's basically a log router as well. And you can customize your own if you're willing to write them. I think it's written in Java, but I'm not sure. Kibana is just a different dashboard that you can use to view indexes that are built in Elasticsearch. So if Graylog can't do everything you need it to do, you can create Kibana dashboards that will dig into the data a little bit deeper. So let's now look at a couple of things that we captured in Graylog. And I'm going to walk around a little bit here because I want to be able to point out what you're looking at. And I hope you can hear me. If you can't hear me, let me know. So I like to walk. I'm better walking than sitting. So basically all of these bars here in this are showing one particular DNS amplification attack that was hitting our network. I don't know what the date was. I've obfuscated, other than the IP addresses there. That's the IP addresses that were sourced. But really that source IP is the target of the attack, right? The DNS packets come in, hit our DNS servers, and they're sent back to that. Because we have tools in place, we're able to see this. We're able to go back and say, oh, that domain right there, that looks fishy, right? So we go back into our aggregated data feeds, we put that domain in a particular data feed, sends it out for DNS servers within 2 minutes. These DNS servers now block all those DNS requests, so we don't participate in that attack. I wish my radio were working here. I wouldn't have to come back up here. So if you look at a little more detail on these DNS amplification attacks, you can see here what will happen. Sometimes you'll see a multitude of different domains being used, but in Graylog you can actually expand the field and look at your quick values, and here you can see the domain 13,000. I don't know what the time frame was. That time frame up there might be, I can't see what that is, 5 minutes. So that's how many DNS queries are being sent within 5 minutes. So that's an anomaly that we can catch. In Graylog, all of these are put into a stream, and we can set a threshold within that stream to alert. So let's say we see any queries for a particular domain reach a threshold of 5 within 1 minute. Should we be alarmed? Yeah, we should be alarmed, right? Nobody needs to ask that many any queries in that short a time. So at that point, we can set an alarm, an alert. We'll get an alert, and we'll be able to go in and investigate and see what's going on with DNS. So we have a dashboard that we run. This dashboard shows us over here. These are the queries coming in, and these are the ones that we're blocking on that side. So we can tell right away when our rules push out new blocks. They show up there within seconds, literally seconds. I can push the rules out to do the blocks, and they'll appear in that list. The other thing we can do is we can see traffic from malicious source IPs. In this case, we know all these were blocked. We're just logging which ones are being blocked so we can see how much traffic we're getting from those particular IPs. These IPs come from data feeds that we update on a regular basis. They're formatted in the right format and pushed out to our F5 load balancers via some TMSH commands. Don't worry about the details of how that works, but they're basically a block list, right? The F5 reads that block list for every incoming DNS request. If it matches, it'll block it. But we're able to see this very quickly when we look at our Graylog information. So in this case, this is showing us, I can't see it on my screen, I'm going to have to walk over here. So this is showing us two different networks, and I don't know if you can see that domain there, but that domain is a malicious domain that was pushing out malware. So we're able to go back over time, put in just that domain name into the query search. Remember I told you to set everything up in name value pairs? Perfect. Very good. All right, so we set everything up in name value pairs, right? So one of the names or one of the values that we can see is over here. The value that we're looking at is source IP. So we called our field source IP. That's the source IP of that particular attack. We can see where that compromise is on a network. Then we can go back to that customer and let them know, hey, you've got an issue here that you need to deal with, and we can help you figure out how to deal with that issue. So, anybody ever looked at Microsoft's DNS debug logs? No, huh? Okay. So you can turn on DNS debug logging, and it will actually take care of all of your DNS logging from Microsoft DNS. The problem with it is, from the GUI, you cannot configure it to roll your logs over. You have to go through PowerShell and do some commands to do that. But once you do that, you can use nxlog to ship that data off. Well, I got a wild hair and said, well, why don't I write a plugin for Graylog that will take this data and make it something that we can read. The cool thing about this is, I'm going to walk around again here. We got green. Good, good. So, over here on this column, we have the domain names, and these are the ones that are no errors. So that's the result of the query. These are basically all queries that are happening on an Active Directory. So these are internal. They're all coming from Active Directory servers in somebody's LAN. So the cool thing is I can go back through changing my queries here, and I can find any domain that I want and attribute that domain lookup back to a particular IP address in my network. So here what we did is we were looking for one particular domain that was causing compromise. You see it came up there X number of times. We can go back through this data here and find out which workstation or device on our network was making that call, and then go back and address that compromised device. So it's a way of grouping our public-facing DNS with our internal DNS, and then giving attribution to whatever device was making those DNS requests in the first place. So the other thing we can do is use maps that are built into Graylog. It'll take, if we set up the geolocation database in Graylog, it will allow us to pinpoint source IP, destination IP, all different kinds of IPs that we're collecting. So we can go look at a map and say, well, we don't have any customers in that part of the world. Why should we be seeing dots show up on the map there, basically, right? So we can see compromise from that perspective as well. One of the other things that we can look at are DNS query response codes. So we can look at the type of DNS queries that are coming in from our network clients and what kinds of responses we're getting. So if we see a large number of NX domain responses, for example, we can go and alert on those and figure out, well, maybe there's something going on here. Maybe somebody's compromised. Maybe they're looking up something that they shouldn't be looking up, and we can act on those. So this is just a quick overview of some of the things that we did. Real quickly before I end, I want to go over some of the things that we do to secure DNS. It might help you in your environment. It might not. You might already do this. I don't know. Just something that we do. We disable DNS access on all WAN interfaces for Microsoft DNS, right? So it's never public facing. One thing that most people don't do, and you probably need to do on your network, you'll see these queries called WPAD queries. Does anybody know what those do? If you don't, you probably want to look and see what they do. Web proxy auto detect queries, right? So what happens if your network sends those out and they get past your AD server and go out to the public network? If somebody compromises your DNS and sends the data back for those, they could then go and set the proxy on your web browsers inside your network to point somewhere where they shouldn't. So these queries are pretty bad. You should use group policy to disable them from your browsers if you can. There's ways to do that in all the different browsers. Use them if you need them, but don't let those queries get out of your network. Use trusted forwarders for your DNS. Trusted forwarders meaning you know who you're forwarding your queries to. Ideally, you would forward them to the root. Or in our case, we get our customers to forward their queries to our SecureSurf servers, which answer the queries or send them to a block page if they're asking for something that they shouldn't be getting to. So know who you're sending your DNS queries to. If you're using a forwarding query, uncheck the box that says send failed queries to the root, right? Because you want to fail secure, not fail open. And configure DNS debug logging so you can see what's going on. Disable users' ability to change their network configuration settings via group policy on their machines, because users never change DNS to get around things, right? They would never think of doing that. Set up audit policies for your DNS entries to make sure that your local Active Directory stuff is the way it should be, that there's not extra things pointing to outside IP addresses, right? Something that people would compromise your DNS, they might throw in a DNS record on your internal AD server that points to an external IP address. That could be really bad, right? So make sure your DNS gets audited on a regular basis, scavenge for stale records. Again, don't host public-facing DNS on an Active Directory AD server. Put your public stuff with a service provider and keep your office stuff separate. What you can do for AD DNS debug logging, here's how you can turn this on and rotate your logs. Use the settings shown here in the picture, and I'll make this slide deck available later to anybody that wants to have access to it. In PowerShell, you have to do a command to enable DNS log rotation, and the commands are there. You can look at the settings by doing the get DNS server diagnostics, and you can use the set DNS server diagnostics to set those three values, and then your logs will roll over. And then in NXLog, you can use it to ship the logs and also tell it how long you want to keep the logs. So you want to roll them off every 14 days or whatever. And then you can use Graylog to visualize it. Disable and lock down your zone transfers on your DNS, right? If you can run this command against your own name servers from the outside, from your home network. Let's say you're on, on your cable network at home. That's bad news, right? Because, hackers can go in there and do the same thing and get all the inside information on your network. Separate your authoritative and recursive servers. Don't use authoritative servers for recursion, ever, never. It's a bad thing, really bad. Force large queries to re-ask on TCP, but limit the rate that those can go at. And then lock down your recursive servers with access lists and firewall rules so that people cannot get to them unless they're allowed. If you want to, you can try to enforce DNSSEC on your primary domains. That's a little bit hard to do. If you want to do that, I suggest using a larger DNS provider like Akamai who can give you the tools to manage that for you. It makes it a little bit easier. Use a DNS filtering service internally to block malicious DNS and monitor your DNS activity. The key to finding compromise on your network is monitoring your DNS activity. It's the first place you're going to see any kind of bad stuff happening. So that's all I've got. Hopefully I didn't keep you too long from your nighttime activities, but if you have any questions, feel free to ask, and I can make the slide deck available anyway. Yes, sir. In our environment, none. We have 300 employees and we run about 1 million queries an hour, and we catch them all. We run our Active Directory domain controllers mostly on virtual machines, but they're all over the globe. There's hundreds of them, so they'll report back. Correct. Full debug log gets you all the query data. Yep. So the question was, what kind of performance hit do Active Directory servers take when you put on the DNS debug logging? And my answer was, we don't see any at all. I mean, there's probably some. You're going to get some disk I/O, but it's minimal. It's not worth. Is there?
Just quick, what was the tool that you mentioned before?
Oh, Elasticsearch is the database? Yep. Yep. Any other questions? Okay, well, I hope you found it informative. Thank you for your time.